While there are many mysteries within astronomy that remain unexplained, there are some that remain completely obscure, even though they have been explained. Today we're unlocking the perplexing secrets of the cosmos, from exploding stars, supermassive black holes, and bizarre jets of gas. Across the world and in space, many high-tech telescopes are picking up the signals that reveal the hidden universe. A fascinating cosmos almost incomprehensible in its size, age, and weirdness. Whilst telescopes have continued to open up mystery after mystery of the universe, scientists are now racing to unlock the latest secrets. In this episode, we've whittled it down to the top 15 biggest and weirdest discoveries in space that change how we see the cosmos. Number 15. Biggest explosion ever seen in the universe. The biggest explosion seen in the universe has been found. This record-breaking gargantuan eruption came from a black hole in a distant galaxy cluster hundreds of millions of light years away. Astronomers made this record-breaking discovery using X-ray data from NASA's Chandra X-ray Observatory and ESA's XMM Newton, and radio data from the Murchison Wide Field Array in Australia and the Giant Meter Wave Radio Telescope in India. The unrivaled outburst was detected in the Ophiuchus galaxy cluster, which is about 390 million light-years from Earth. Galaxy clusters are the largest structures in the universe held together by gravity, containing thousands of individual galaxies, dark matter, and hot gas. In the center of the Ophiuchus cluster, there's a large galaxy that contains a supermassive black hole. Researchers have traced the likely source of this gigantic eruption to this black hole. Although black holes are famous for pulling material toward them, they often expel prodigious amounts of material and energy. This happens when matter falling toward the black hole is redirected into jets or beams that blast outward into space and slam into any surrounding material. Astronomers need to combine the X-ray information along with the radio data in order to clinch this finding. They discovered that a cavity in the hot gas, first seen in the Chandra data in 2016, was filled almost perfectly with radio emission created by electrons that had been accelerated to nearly the speed of light. This allowed them to confirm that an explosion of unprecedented size took place in Ophiuchus. The amount of energy required to create the cavity in Ophiuchus is about 5 times greater than the previous record holder, MS 735 plus 74. And hundreds and thousands of times greater than typical clusters. The black hole eruption must have finished because the researchers do not see any evidence for current jets in the radio data. This shutdown can be explained by the Chandra data, which shows that the densest and coolest gas seen in X-rays is currently located at a different position from the central galaxy. If this gas shifted away from the galaxy, it will have deprived the black hole of fuel for its growth, turning off the jets. While much has been learned about the galaxy cluster Ophiuchus through X-ray and radio telescopes, more data will be needed to answer the many remaining questions this object poses. Number 14. Cosmic Jekyll and Hyde. A double star system has been flipping between two alter egos according to observations with NASA's Chandra X-ray Observatory and the NSF's Carl F. Jansky Very Large Array, VLA. This is a rare example of a cosmic object changing its behavior in this way. Astronomers found this unusual object in a dense collection of stars, the globular cluster Terzan 5, which is located in the Milky Way galaxy about 20,000 light-years from Earth. One object among the millions in the cluster that caught the attention of astronomers is an especially volatile example of a double or binary system. This stellar duo has a neutron star, the extremely dense remnant left behind by a supernova explosion, in close orbit around a star like the Sun, but with less mass. This binary system is known as Terzan 5 CX1 and is labeled in the Chandra image of this cluster. Using X-ray data from Chandra that spans nearly a decade and a half, researchers noticed that the Terzan 5 CX1 behaved like one type of object before changing its identity and then years later returned to its original role. In binary systems like Terzan's 5 CX1, the heavier neutron star pulls material from the lower mass companion into a surrounding disk. Astronomers can detect these so-called accretion disks by their bright X-ray light and refer to these objects as low-mass X-ray binaries. Spinning material in the disk falls onto the surface of the neutron star, increasing its rotation rate. The neutron star can spin faster and faster until the roughly 10-mile-wide sphere packed with more mass than the Sun is rotating hundreds of times per second. Eventually, the transfer of matter slows down and the remaining material is swept away by the whirling magnetic field of the neutron star, which becomes a millisecond pulsar. While scientists expect the complete evolution of a low-mass X-ray binary into a millisecond pulsar should happen over several billion years, there's a period of time when the system can switch rapidly between these two states. Chandra and VLA data taken between 2003 and 2016 showed that Terzan 5 CX1 has gone from acting like a low-mass X-ray binary to acting like a millisecond pulsar and then back again. Astronomers will continue to watch this unusual system with Chandra and other telescopes to see what other stories this object must tell. Number 13. Black hole jet in M87. Using NASA's Chandra X-ray Observatory, astronomers have seen that the famous giant black hole in Messier 87, or M87, is propelling particles at speeds greater than 99% of the speed of light. The Event Horizon Telescope collaboration released the first image of a black hole with observations of Messier 87 last April, making it arguably the universe's most famous black hole. Meanwhile, astronomers have studied a jet of high-energy particles powered by the black hole blasting out of the center of M87 in radio, optical, and X-ray light for many years. Over its 2 decades of operations, Chandra has observed M87 many times. And now, researchers use Chandra's data to determine that sections of the jet in M87 are moving at nearly the speed of light. While astronomers have observed features in the M87 jet blasting away from its black hole this quickly at radio and optical wavelengths for many years, this provides the strongest evidence yet that actual particles are traveling this fast. When matter gets close enough to a black hole, it enters a swirling pattern called an accretion disk. Some material from the inner part of the accretion disk falls into the black hole, and some of it's redirected away from the black hole in the form of narrow beams or jets of material along magnetic field lines. Because the material can fall onto the black hole erratically, the jets are made of clumps or knots that can sometimes be identified with Chandra and other telescopes. A team of astronomers recently used Chandra's observations from 2012 and 2017 to track the motion of 2 X-ray knots located within the jet about 900 and 2500 light-years away from the black hole. The X-ray data show motion with apparent speeds of 6.3 times the speed of light for the X-ray knot closer to the black hole and 2.4 times the speed of light for the other. While this sounds like it breaks the laws of physics, it's actually an illusion that occurs when objects are traveling close to the speed of light along a direction that is close to our line of sight. The jet travels almost as quickly towards us as the light it generates, giving the illusion that the jet's motion is much more rapid than the speed of light. In the case of M87, the jet is pointing close to our direction, resulting in these exotic apparent speeds. The Chandra data are an excellent complement to what the Event Horizon Telescope, or EHT, found. The jet Chandra sees is 500,000 times larger in size than the ring imaged by the EHT. Another difference is that the EHT observed M87 over 6 days in April 2017, giving a recent snapshot of the black hole. The Chandra observations investigate ejected material within the jet that was launched from the black hole hundreds and thousands of years earlier. Astronomers are looking forward to seeing what else these telescopes can learn about black holes in the years to come. Number 12. The Crab Nebula 3D Visualization. In the year 1054 AD, Chinese skywatchers witnessed the sudden appearance of a new star in the heavens, which they recorded as 6 times brighter than Venus, making it the brightest observed stellar event in recorded history. This guest star, as they described it, was so bright that people saw it in the sky during the day for almost a month. Native Americans also recorded its mysterious appearance in petroglyphs. Observing the nebula with the largest telescope of the time, Lord Rosse in 1844 named the object the crab because of its tentacle-like structure. But it wasn't until the 1900s that astronomers realized the nebula was the surviving relic of the 1054 supernova, the explosion of a massive star. Now, astronomers and visualization specialists have combined the visible, infrared, and X-ray vision of NASA's great observatories to create a three-dimensional representation of the dynamic Crab Nebula. Certain structures and processes driven by the pulsar engine at the heart of the nebula are best seen at particular wavelengths. The multi-wavelength computer graphics visualization is based on images from the Chandra X-ray Observatory and the Hubble and Spitzer space telescopes. The new video dissects the intricate nested structure that makes up this stellar corpse, giving viewers a better understanding of the extreme and complex physical process powering the nebula. The powerhouse engine energizing the entire system is a pulsar, a rapidly spinning neutron star. The superdense, crushed core of the exploded star, the tiny dynamo, is blasting out blistering pulses of radiation towards us 30 times a second with unbelievable clockwork precision. The visualization is one of a new generation of products and experiences being developed by NASA's Universe of Learning program. It helps illustrate the power of what astronomers call multi-wavelength astronomy, where different types of light are combined to get a more complete understanding of the universe and objects within it. Number 11. Galaxy gathering brings warmth. Using NASA's Chandra X-ray Observatory and other telescopes, a team of astronomers has studied two galaxy groups that are smashing into each other at a remarkable speed of about 4 million miles per hour. This could be the most violent collision yet seen between two galaxy groups. The system is called NGC 6338, which is located about 380 million light-years from Earth. The majority of galaxies do not exist alone, rather they are bound to other galaxies through gravity, either in relatively small numbers, known as galaxy groups, or much larger concentrations called galaxy clusters of hundreds or thousands of galaxies. And sometimes these collections of galaxies themselves are drawn toward one another by gravity and eventually merge. By studying systems like NGC 6338, astronomers are trying to better understand how some of the very biggest objects in the universe grow and evolve over time. The researchers in this study estimate that the total mass contained in NGC 6338 is about 100 trillion times the mass of the Sun. This significant heft, roughly 83% of which is in the form of dark matter, 16% is in the form of hot gas, and 1% in stars, indicates that this galaxy group is destined to become a galaxy cluster in the future. This will be its fate as the collision and merger in NGC 6338 is completed and the system continues to accumulate more galaxies through gravity. Number 10. Black hole nurtures baby stars a million light-years away. Astronomers have uncovered a black hole that may have sparked the birth of stars over a phenomenal distance of more than 1 million light-years and across multiple galaxies. If confirmed, this discovery, made with NASA's Chandra X-ray Observatory and other telescopes, would represent the widest reach ever seen for a black hole, acting as a stellar kickstarter. The supermassive black hole is located in the center of a galaxy about 9.9 billion light-years from Earth. This galaxy has at least 7 neighboring galaxies, according to 2 optical light telescopes in Chile and Arizona. Previously, astronomers had discovered a jet from this black hole in radio waves with the Very Large Array. Using Chandra, researchers then detected a bright X-ray source around the black hole as well as a diffuse cloud of X-rays at one end of the jet. Astronomers think this thin cloud of X-rays probably represents a bubble in the galaxy's hot gas created by the jet. As this bubble expanded, it likely created a shock wave that triggered star formation as it moved. Researchers estimate from their data that 4 neighboring galaxies, each about 400,000 light-years away from the end of the black hole's jet, have dramatically increased rates of star formation. This result represents a relatively rare occurrence where a black hole is actually boosting star formation rather than suppressing it. On top of that, this is the farthest that astronomers have ever seen this effect of so-called positive feedback extend. Scientists will continue to study objects similar to this one in the hopes of trying to determine if this phenomenon is common or not in the formation of groups and clusters of galaxies. Number 9. The Phoenix Cluster. Astronomers have confirmed the first example of a supermassive black hole unable to prevent copious numbers of stars from forming in the core of the galaxy cluster where it resides. This result provides new details about the life cycles of some of the most extreme objects in the universe. Galaxy clusters are the largest structures in the cosmos that are held together by gravity and consist of hundreds or even thousands of galaxies embedded in hot gas and invisible dark matter. The largest supermassive black holes astronomers have ever found are in the centers of galaxy clusters. For decades, astronomers thought galaxy clusters should contain rich nurseries of stars in their centers, resulting from cooling of their huge reservoirs of hot gas. Instead, they found the powerful giant black holes were pumping out energy via jets and keeping the gas too warm to form many stars. Now scientists have compelling evidence that stars are forming at a furious rate in the Phoenix galaxy cluster, apparently linked to a less effective black hole in its center. In this unique cluster, outbursts from the central black hole instead appear to be abiding in the formation of stars. They used new data from NASA's Chandra X-ray Observatory and Hubble Space Telescope and the NSF's Carl Jansky Very Large Array, or VLA, to build on previous observations of this cluster. Data from Chandra show that the coolest gas it can detect is located near the center of the cluster. In the absence of significant sources of heat, astronomers expect cooling to occur at the highest rates in a cluster's center, where the densest gas is located. Outbursts powered by the black hole then forced the gas to cool even more quickly. The outburst drove a pair of jets seen in radio waves by the VLA, which pushed outward and inflated cavities in the hot gas, detected with Chandra. Filaments of cool gas observed by Hubble are located around the borders of the cavities, so the authors concluded that the black hole's outburst carried the gas away from the black hole. The farther away from the black hole, the faster the gas can cool to form stars. This latest result on the Phoenix cluster demonstrates that the supermassive black holes at the centers of galaxy clusters can have dramatic and different impacts on their surroundings. Astronomers will continue to use Chandra and other telescopes to learn more about the Phoenix cluster and other cosmic giants like it. Number 8. Collision between 4 galaxy clusters in Abell 1758. When 2 pairs of galaxy clusters collide, the final result is not 4 separate objects, but one giant galaxy cluster. Astronomers using data from NASA's Chandra X-ray Observatory and several other telescopes have put together a detailed map of a rare collision between 4 galaxy clusters. This megastructure is being assembled in the system called Abell 1758, located about 3 billion light-years from Earth. Eventually, all 4 clusters, each with a mass of at least several hundred trillion times that of the Sun, will merge to form one of the most massive objects in the universe. Galaxy clusters are the largest structures held together by gravity. They consist of hundreds or even thousands of galaxies embedded in hot gas and contain an even larger amount of unseen dark matter that gravitationally dominates the cluster. Sometimes 2 galaxy clusters collide, as in the case of the Bullet cluster, and occasionally more than 2 will collide in the same time frame. The Chandra data revealed for the first time a shockwave similar to the sonic boom from a supersonic aircraft in hot gas in the northern pairs collision. From this shockwave, researchers of the new study estimated 1 pair of clusters are moving relative to each other at a speed between 2 and 3 million miles per hour. Chandra also provides information about how elements heavier than helium in the cluster's hot gas get mixed up and redistributed after galaxy clusters collide and merge. Because this process depends on how far a merger is progressed, Abell 1758 offers a valuable case study since the 2 pairs of clusters are at different stages of merging. The new Abell 1758 result shows the further along a merger is, the farther away from the centers of the clusters these important heavy elements are found. Number 7. Tycho's supernova remnant. In 1572, the Danish astronomer Tycho Brahe was among those who noticed a new bright object in the constellation of Cassiopeia. Adding fuel to the intellectual fire that Copernicus started, Tycho showed this new star was far beyond the moon and that it was possible for the universe beyond the sun and planets to change. Astronomers now know that Tycho's new star was not new at all. Rather, it signaled the death of a star in a supernova, an explosion so bright that it can outshine the light from an entire galaxy. This particular supernova was called Type La, which occurs when a white dwarf star pulls material from or merges with a nearby companion star until a thermonuclear explosion is triggered. The white dwarf star is obliterated, sending its debris hurtling into space. As with many supernova remnants, the Tycho supernova remnant, as it's known today, glows brightly in X-ray light because shock waves, similar to sonic booms from supersonic aircraft generated by the stellar explosion, heat the stellar debris up to millions of degrees Celsius. In its 2 decades of operation, NASA's Chandra X-ray Observatory has captured unparalleled X-ray images of many supernova remnants. In the Tycho supernova remnant, Chandra reveals an intriguing pattern of bright clumps and fainter holes. What caused this thicket of high-energy knots in the aftermath of this explosion? Did the explosion itself cause this clumpiness, or was it something that happened afterward? To emphasize the clumps in the image and the three-dimensional nature of Tycho, 2 narrow ranges of X-ray energies were selected to isolate material moving away from Earth and moving toward us. The other colors in the image show a broad range of different energies and elements and a mixture of directions of motion. By comparing the Chandra image of Tycho to 2 different computer simulations, researchers were able to test their theoretical ideas against actual data. They found that it's most likely that the clumps came from the explosion itself. While scientists are not sure how, one possibility is that the star's explosion had multiple ignition points, like dynamite sticks being set off simultaneously in different locations. Understanding the details of how these stars explode is important because it may improve the reliability of the Type La supernovas as standard candles for cosmological studies. These supernovas also sprinkle elements such as iron and silicon that are essential for life as we know it into the next generation of stars and planets. Number 6. GSN 069, Supermassive Black Hole. There's an old adage that it's not healthy to skip meals. Apparently, a supermassive black hole in the center of a galaxy millions of light years away has gotten the message. A team of astronomers found X-ray bursts repeating at about every 9 hours, originating from the center of a galaxy called GSN 069. Obtained with NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton, this data indicates that the supermassive black hole located there is consuming large amounts of material on a regular schedule. While scientists had previously found 2 stellar mass black holes, those that weigh about 10 times the Sun's mass, occasionally undergoing regular outbursts before, this behavior has never been detected from a supermassive black hole until now. The black hole at the center of GSN 069, located 250 million light years from Earth, contains about 400,000 times the mass of the Sun. The researchers estimate that the black hole is consuming about 4 moons worth of material about 3 times a day. That's equivalent to almost 1 billion pounds going into the black hole per feeding. ESA's XMM Newton was the first to observe this phenomenon in GSN 069 with the detection of 2 bursts on December 24, 2018. Astronomers then followed up with more XMM Newton observations on January 16th and 17th, 2019, and found 5 outbursts. Observations by Chandra less than a month later on February 14th and 15th revealed an additional 3 outbursts. The Chandra data were crucial for this study because they were able to show that the X-ray source is located in the center of the host galaxy, which is where a supermassive black hole is expected to be. The combination of data from Chandra and XMM Newton implies that the size and duration of the black hole's meals have decreased slightly and the gap between the meals has increased. Astronomers are planning future observations that will be crucial to see if the trend continues. Number 5. Cassiopeia A, first light to 20 years later. Over its 2 decades in space, NASA's Chandra X-ray Observatory has captured many spectacular images of cosmic phenomena. But perhaps its most iconic is the supernova remnant called Cassiopeia A. Located about 11,000 light-years from Earth, Cass A, as it's nicknamed, is the glowing debris field left behind after a massive star exploded. When the star ran out of fuel, it collapsed onto itself and rebounded explosively as a supernova, possibly briefly becoming one of the brightest objects in the sky. The shock waves generated by this blast supercharged the stellar wreckage and its environment, making it glow brightly in many types of light, particularly X-rays. Shortly after Chandra was launched aboard the Space Shuttle Columbia on July 23, 1999, astronomers directed the observatory to point toward Cass A. The result was a seminal moment for the observatory and the field of X-ray astronomy with the release of Chandra's first light image on August 26, 1999. Since then, Chandra has repeatedly returned to Cass A to learn more about this important object. A new movie shows the evolution of Cass A over time, enabling viewers to watch as 10 million degrees Celsius gas in the remnant expands outward. This X-ray data has been combined with data from another of NASA's great observatories, the Hubble Space Telescope, showing delicate filamentary structures of cooler gases with temperatures of about 10,000 degrees Celsius. In this movie, we see Hubble data from a single time period to emphasize the changes in Chandra data. The movie shows Chandra observations from 2000 to 2013, or about the time it takes a child to enter kindergarten, then graduate from high school. This gives astronomers a rare chance to watch as a cosmic object changes on human timescales, giving them new insight into the physics involved. For example, particles in the blue outer shock wave carry more energy than those produced by the most powerful particle accelerators on Earth. As this blast wave hits material in its path, it slows down, sending a shock wave backwards at speeds of millions of miles per hour. Chandra will continue to observe Cassiopeia A in the future, adding to its remarkable legacy of discovery for this supernova remnant. Number 4. PSO 16713. Astronomers have discovered evidence for the farthest cloaked black hole found to date using NASA's Chandra X-ray Observatory. At only about 6% of the current age of the universe, this is the first indication of a black hole hidden by gas at such an early time in the history of the cosmos. Supermassive black holes, which are millions to billions of times more massive than our Sun, typically grow by pulling in material from a disk of surrounding matter. Rapid growth generates large amounts of radiation in a very small region around the black hole. Scientists call this extremely bright, compact source a quasar. According to current theories, a dense cloud of gas feeds material into the disk surrounding a supermassive black hole during its period of early growth, which cloaks or hides most of the quasar's bright light from our view. As the black hole consumes material and becomes more massive, the gas in the cloud is depleted until the black hole and its bright disk are uncovered. The new finding came from observations of a quasar called PSO 16713, which was first discovered by PanSTARRS, an optical light telescope in Hawaii. Optical observations from these and other surveys have detected about 180 quasars already shining brightly when the universe was less than 1 billion years old, or about 8% of its present age. These surveys were only considered effective at finding unobscured black holes because the radiation they detect is suppressed by even thin clouds of gas and dust. Since PSO 16713 was part of those observations, this quasar was expected to be unobscured too. A team of researchers, however, used Chandra to find something different. They observed PSO 16713 and 9 other quasars with Chandra that had been discovered with optical surveys. After 16 hours of observation, only 3 X-ray light particles were detected from PSO 16713, all with relatively high energies. Since low-energy X-rays are more easily absorbed than higher-energy ones, the likely explanation is that the quasar is highly obscured by gas, allowing only high-energy X-rays to be detected. This means that PSO 16713 quasar may be the most distant cloaked supermassive black hole yet seen at 850 million years after the Big Bang. The previous record holder has been observed 1.3 billion years after the Big Bang. The researchers plan to follow up with more observations to learn more about PSO 16713 and also to try to use Chandra to find other systems like it. Number 3. Lensed quasars. Like whirlpools in the ocean, spinning black holes in space create a swirling torrent around them. However, black holes do not create eddies of wind or water, rather they generate disks of gas and dust heated to hundreds of millions of degrees that glow in X-ray light. Using data from NASA's Chandra X-ray Observatory and chance alignments across billions of light years, astronomers have deployed a new technique to measure the spin of 5 supermassive black holes. The matter in one of these cosmic vortices is swirling around its black hole at greater than 70% of the speed of light. The astronomers took advantage of a natural phenomenon called gravitational lens. With just the right alignment, the bending of space-time by a massive object such as a large galaxy can magnify and produce multiple images of a distant object, as predicted by Einstein. In this latest research, astronomers used Chandra and gravitational lensing to study 6 quasars, each consisting of a supermassive black hole rapidly consuming matter from a surrounding accretion disk. Gravitational lensing of the light from each of these quasars by an intervening galaxy has created multiple images of each quasar. The key advance made by researchers in this study was that they took advantage of microlensing, where individual stars in the intervening lensing galaxy provided additional magnification of the light from the quasar. A higher magnification means a smaller region is producing the X-ray emission. How can these black holes spin so quickly? The researchers think that the supermassive black holes likely grew by accumulating most of their material over billions of years from an accretion disk spinning with a similar orientation and direction of spin rather than from random directions. Like a merry-go-round that keeps getting pushed in the same direction, the black holes keep picking up speed. This information helps astronomers learn more about how these supermassive black holes grew and evolved in the early universe. Number 2. The Coma Cluster. Many of us have seen intricate patterns that milk makes in coffee and much smoother ones that honey makes when stirred with a spoon. Which of these cases best describes the behavior of the hot gas in galaxy clusters? By answering this question, a new study using NASA's Chandra X-ray Observatory has deepened our understanding of galaxy clusters, the largest structures in the universe held together by gravity. Gravity clusters are comprised of 3 main components: individual galaxies, multi-million degree gas fills the space between the galaxies, and dark matter, a mysterious form of matter that's spread throughout a cluster and accounts for about 80% of the mass of the cluster. A team of astronomers used a new 12-day-long Chandra observation of the Coma galaxy cluster to probe its hot gas, which glows only in X-ray light. By measuring the behavior of the hot gas on small scales, the researchers were able to learn about the viscosity, the technical term for stickiness, of the hot gas in Coma. They found that the viscosity of Coma's gas was lower than they expected. In other words, the hot gas in Coma behaves more like milk than honey in our cosmic coffee mug. Why is the viscosity of Coma's hot gas so low? Scientists are still working on that question, but one possible explanation is that tiny irregularities in Coma's magnetic field create turbulence in the hot gas. These small-scale properties can, in turn, have major impacts on important phenomena such as collisions and mergers with other galaxy clusters and galaxy groups. Scientists will continue to study galaxy clusters with Chandra to get a deeper understanding of these cosmic giants. Number 1. MRK 1216. Isolated for billions of years, a galaxy with more dark matter packed into its core than expected has been identified by astronomers using data from NASA's Chandra X-ray Observatory. The galaxy, known as Markarian 1216, contains stars that are within 10% of the age of the universe. In other words, the stars are almost as old as the universe itself. Scientists have found that Markarian 1216 has gone through a different evolution than typical galaxies. This includes dark matter that, through gravity, holds the galaxy together. Dark matter is a mysterious substance that accounts for about 85% of the matter in the universe, yet does not give off or reflect light. Therefore, scientists have only been able to detect it indirectly so far, making it a challenge to learn about. Markarian 1216 belongs to a family of elliptically shaped galaxies that are more densely packed with stars in their centers than most other galaxies. Astronomers think they've descended from reddish, compact galaxies called red nuggets that formed about 1 billion years after the Big Bang, but then stalled in their growth about 10 million years ago. If this explanation is correct, then the dark matter in Markarian 1216 and its galactic cousins should be tightly packed. To test this idea, for the first time, a pair of astronomers studied the X-ray brightness and temperature of hot gas from Chandra at different distances from Markarian 1216's center. This allowed them to, in a sense, weigh how much dark matter exists in the middle of the galaxy. The researchers found a high concentration of dark matter in the center of Markarian 1216, confirming that Markarian 1216 descended from a red nugget galaxy. This tells us about the evolution of MRK 1216 going back in time about 10 billion years. Further studies of this galaxy may provide astronomers with the opportunity to test ideas about the nature of dark matter.